neuroscience is in the field of computer vision. We associate any problem that has an image or camera input to encompass problems within computer vision. Self-driving cars, fMRI analysis, Mars exploration rovers, facial recognition systems, object detection, and augmented reality are just a few breakthroughs in the field. In this video, we will take a look at a new type of neural network architecture called masked region-based convolutional neural networks, masked RCNN for short, and in the process highlight some key subproblems in computer vision as well. Masked RCNN works towards the problem of instance segmentation, the process of detecting and delineating each distinct object of interest in an image. And so, instance segmentation is a combination of two subproblems. The first is object detection, and this is the problem of finding and classifying a variable number of objects in an image. They are variable numbered because the number of objects detected in an image can vary image to image. And the second part of instance segmentation is semantic segmentation. Semantic segmentation is the understanding of an image at the pixel level. That is, we want to assign an object class to each pixel in the image. In this figure with the motorcyclist, apart from recognizing the bike and the person riding it, we also have to delineate the boundaries of each object. Using object detection and semantic segmentation together, we get instance segmentation. In these images, the bounding box is created from object detection, and the shaded masks are the output of semantic segmentation. Now that we have a high-level intuition of instance segmentation, we'll take a look at the architecture behind masked RCNN. Since there are two phases, we have two parts. For object detection, it uses an architecture similar to faster RCNNs. For semantic segmentation, it uses fully convolutional networks. So first off, what is an RCNN? It is an approach to bounding box object detection, thus creating a number of object regions, or regions of interest, ROIs. The next version, faster RCNN, performs a better job by incorporating an attention mechanism using a region proposal network, an RPN. Faster RCNN performs object detection in two stages. First, determine the bounding box and hence determining the regions of interest. This is done using the RPN protocol, like I just said before. And second, for each ROI, we determine the class label of the object. This is done with ROI pooling. Masked RCNN does incorporate these tasks, but there's a problem of data loss in ROI pooling. This involves the applying of pooling, usually max pooling, on a region of interest, the bounding box computed during object detection. Hence the name ROI pool. In this method, the stride is quantized. Now, pooling is used for downsampling of features and is used to introduce invariance to minor distortions in input. These minor distortions could be something as simple as rotation of an image. So consider this 5, but even if it is rotated, our models should still consider this image as a 5. That is the same input. So pooling enables the model to become invariant to such rotation in this case. Stride is the number of cells by which we move our sliding window during pooling, or during convolution. If you want more information about pooling and the intuition on stride, check out my video on convolution neural networks. Now coming back to ROI pooling. When I say that the stride is quantized, what do I mean? Consider a region of interest of say 17 x 17, and we need to map it to a space of 7 x 7. The required stride is 17 divided by 7, which is 2.42. Since a stride of 2.42 is meaningless, ROI pooling will quantize this value by rounding it down to 2. So it will use a stride of 2 along the width and the height. However, in doing so, it only considers the top 14 x 14 pixels in the 17 x 17 region. The remaining points are lost. Not only is there a loss of data, but this can also lead to misalignment. If we use an 18 x 18 input and map it to a 7 x 7 output, the required stride becomes 2.57. This rounds up to 3 in ROI pooling, so you can see that there's a misalignment when we perform pooling here. Now, to address this problem, ROI align is used. No quantization takes place, So in the case of the 17x17 input region, we consider a 2.42 stride as it is. However, this value is meaningless. Each cell is divided into a 2x2 bin, so that creates 4 regions in the top left, the top right, the bottom left, and the bottom right. And each of these subcells is pooled through bilinear interpolation, leading to 4 values per cell. And the final cell value is then computed by either an average or the maximum over the 4 sub-values. By addressing the loss and misalignment problems of ROI pooling, the new ROI align leads to improved results. ROI align is thus better than ROI pool, as it allows us to preserve spatial pixel-to-pixel alignment for every region of interest, and there is no information lost, as there is no quantization. Conceptually, the masked RCNN is similar to the faster RCNN. Masked RCNN additionally outputs the object mask using pixel-to-pixel alignment. This mask is a binary mask outputted for each region of interest. Much overhead isn't incurred when computing this mask, as it is done in parallel with the bounding box creation and classification. Consider a region of interest of m cross m pixels. Let's assume that there's k possible objects that it could be. For example, in an image, if we were trying to categorize humans, dogs, and cats, then k would be equal to 3. For each type k, a binary mask m cross m is constructed, analogous to a one versus rest approach. Hence, while computing the mask, a loss of km square is incurred. This is different from the typical approach of constructing a single mask from k classes, as the classes would compete in the mask. This lack of competition is the key to good performance in instance segmentation. In each region of interest, ROI, determined in the object detection phase, let's take a look at the semantic segmentation with FCNs, fully convolution networks. FCNs are used to predict the mask from each ROI. So why are we using convolutional layers? This is because convolution layers retain spatial orientation. Such information is crucial for location-specific tasks like creating an object mask. So you can see why the traditional use of fully connected layers won't work here. In fully connected layers, the spatial orientation of pixels with respect to each other is lost, as they are squished together to form a feature vector. In Facebook AI research, the COCO dataset is used. It's a large-scale dataset for object detection, segmentation, and captioning. There are over 200,000 labeled images consisting of 1.5 million objects. Masked RCNN takes about 1 to 2 days to train on this dataset using an 8 GPU machine. It achieves good results even for challenging images. Here's a comparison with respect to the state-of-the-art fully convolution instance segmentation system, FCIS. FCIS is an alternate framework that also uses semantic segmentation and object detection to categorize, box, and mask objects in an image, and it does it fast. But FCIS exhibits systematic errors on overlapping instances and creates spurious edges, showing that it is challenged by the fundamental difficulties of segmenting instances. Here are some key things to remember. Instance segmentation is object detection with semantic segmentation. Masked RCNN is an architecture to achieve instance segmentation. It combines faster RCNNs with fully convolution networks, FCNs. Masked RCNN uses ROI align, which preserves the spatial orientation of features and leads to no loss of information. And there's that, the new masked RCNN for instance segmentation. I'll leave a link to the main paper, their code, and links to other cool blog posts and papers in the description down below. So check that out too. Leave a like and comment down below on your thoughts on this new technology. Subscribe to the channel for more super duper content, and I will see you in the next one. See you! Subscribe. Please